Okay. Oh, that's good. Frozen. There we go. Hey. Okay. All right, guys. So these are going to be the work notes. So if you look kind of up there in the top, whoop, see that? Work notes. So that can be the title. If we are going to do an essential question for these notes, okay, EQ. Um, we would want to do something like, how can I calculate the amount of work done? If we walk away from these notes just understanding how to calculate work done, then that's going to be good. That's really the main thing that we want to get towards. Now, before we start talking about calculating work done, I do want to just real quickly redefine work. Okay, so let's remember that the amount, or work is the amount of energy um, transferred into or out of a system. Okay, so it can be the amount of energy transferred into or out of a system. Um, and then beyond that, I want to add this second little note, okay? And so the way that we recognize work, okay? Work happens when a force moves something, all right? So when I say that, what's really important for us to remember here is that the force has to move the object. The object, so for instance, if I push against a wall, I might apply a force to the wall, but if I don't move it, I'm not doing work, okay? So this move is a really important part of what defines work. Work has to move something, okay? All right, so let's talk about, we just finished a lab, and in the lab, we actually calculated work, okay? And when the place where we calculated work is when we multiplied the distance or the length times the average force. So the main equation that we want to start off with here, okay, is that work equals force times delta x. And so remember that uh, um, F equals force, and delta x is just going to be the distance moved. Okay, so it's the force. Zoom for me. Uh-oh. I didn't mean to put that there. Zoom for me. Okay. All right. So it's the force acted multiplied by the distance. So force times distance. Um, and at this point, I also want to just go ahead and talk about units. Okay. Because if force is in newtons and then distance, we would always measure distance in meters, then that means that W, which is work, okay? Well, that's got to be measured in newtons times meters, which we actually have a name for newtons times meters, or joules, okay? So joule equals newtons times meters. So we now have a unit that we can use for energy and for work. Remember, work is just an amount of energy. So 1 joule is just 1 Newton times 1 meter. Okay, so we've got that. Now, let's talk about calculating. So you can use that equation to calculate force, but you can only do it when the force is constant. So in our lab, we had constant force. What I want to do is I want to show you guys an alternative method to calculating here, and I want to make a graph. So, sorry, I'm going to go back to my little drawer thing here. Oh man, Okay, so if we think about graphing what we measured in our lab, it'd look something like this. So I would have a graph, and down here, I'm going to label this as x, which is distance, measured in meters. And over here, I'm going to label this as force, measured in newtons. Now, in our lab, our forces were constant. Remember, we pull with a constant speed. So the force acted like that. And let's just pretend that we're talking about like the 50 centimeter, or oh, let's do it this way. Let's say we're using the 100 centimeter board. So we'd go from like 0 to 1 meter. Notice that this is in meters, not centimeters. So we go 0 to 1 meter. Now, the way that we would calculate the work done here would be to calculate the area. So over here, I'm going to do calculate area under the line. And I'm going to go ahead and I'm going to highlight area under the line. Okay? And so we're talking about calculating the size of, I'll use a different color, this box. Okay? Now to do that, to calculate the area of a rectangle, I'm going to go area equals length times width. Whoa, that got weird. Okay? And really, I'm going to call it something else. I'm going to do height times base. So area is going to be base times height, like that. Okay? What we see, though, is that really this height is the same as force. Okay? So really, it's area equals force times, and then this base is the same as the change in x, so really it's force times delta x. So to calculate the area under the line, I'm really not doing anything different than I would do with this equation, because it's still just force times delta x. Now, the reason I wanted to show you this area under the line calculation is because sometimes we might get changing force. So I might see something, okay, if I've got x, zoom in a little bit. So we saw that. Sorry, guys. So if I've got force and I've got distance, what if I don't have constant force? So what if I start off with no force and then my line goes up? And so gradually, as I push my object farther, I increase the amount of force. Well, I can't just use this force times delta x anymore. That doesn't work because my force isn't constant. If I did that, don't draw this. Do not draw right now. Stop drawing. If I did the force times delta x, I'd be calculating the area of a box. And a box isn't what I want. What I want is the area of a triangle. So now I'm trying to calculate this. So the area of a triangle is once again base times height, but notice that it's only half of that box. So I'm going to divide that by 2. All right, so that's base times height divided by 2. Okay? So I don't have an example for you right now in the notes, but you are going to have a worksheet to work on some of these things. So area of a triangle, make sure that we've got that thing, base times height divided by 2. We want that highlighted. We also want this one highlighted because you have to do both things in your worksheet. All right, good job, guys.